Thank you very much, first of all, for inviting me to give this interview and the talk in the near future. My name is Massimo Ferrario. I'm working at INFN in Frascati, and I've been working for my entire career in the development of high brightness beams, especially from photoinjectors, driving free electron lasers. And more recently, I start also to investigate the problems related to plasma acceleration. I'm member of the EuPRAXIA collaboration since the very beginning, and I'm also happy to have done a contribution to bring a part of EuPRAXIA here in Frascati, where I am leading, by the way, I'm coordinating the effort to build here the beam-driven pillar of the EuPRAXIA collaboration. And in particular, in these days, we are working on the preparation of the technical design report. Plasma acceleration is really a very challenging opportunity because the main expectation is to be able to build a compact and less expensive accelerator. This is still to be demonstrated at the end because the theory help us to go in this hope, but in reality then you have to face with many other problems that has to be demonstrated now. Application of accelerators are a long list of possibility, from medical to biological to fundamental physics application, radiation sources. So the possibility to have a compact and less expensive accelerator is certainly a very good possibility. And this is a challenge that we are facing now. So EuPRAXIA should be a dream close to reality to demonstrate the effectiveness of plasma accelerators. Challenging essentially is the interaction of the beam with the plasma itself. And in order to keep the quality of the electron beam good enough to not only to be accelerated, but also downstream to drive experiments. So what is new, what we expect in the near future is to demonstrate the good matching with the accelerated beam and the plasma. And this is still an important topic to demonstrate. In addition, the plasma module must be integrated in a conventional machine because we need a LINAC or a laser to drive the plasma wave. Then we need a transport line to go towards the experimental hole. And this is a difficult topic because the beam goes through different regimes along the machine and must be preserved its quality. And this is really a quite difficult task. This is a difficult question because I don't think there is already now a final answer. Our choice to focus on the beam-driven is motivated essentially by one local reason, that is Frascati has a long-standing experience in radio frequency LINACs. So for us to use a LINAC to drive a plasma, it was more natural than the laser-driven, but for us is still a new topic, even if we have now a good group working on this subject. But in addition, there is some advantage. The advantage is, for example, that ref LINACs already now can provide high repetition rate, higher than the one that you can obtain with the laser-driven case. And then the beam is less sensitive to some typical problem of the laser-driven, that is, for example, the shift with respect to the phase of the acceleration with respect to the laser, because both the electron beam driver and the electron beam witness travel at the same speed inside the plasma. And so there is no dephasing like can occur in the laser plasma facility, where a laser group velocity in the plasma is much less than the velocity of light. On the other hand, Linux are quite still a long machine. So you lose a little bit in the compactness with respect to the laser. But I think that the advantages are good, because high repetition rate is a fundamental request for future operation of user facilities. And I'm confident that plasma beam driven could offer an important solution.